Okay, so we've got the presentation to go through, but in a slightly different tack. Some of these presentations are then taught slides followed by the CoLab lab book to go through. This one, actually, the slides kind of mirror the CoLab book. So I'll just get the CoLab notebook up full screen. So this CoLab notebook goes along and does the data wrangling aspects at the same time as the slides do. So what I'd invite you to do, if you're feeling confident enough to go for it, then I'd invite you to go to this CoLab notebook and make a start yourself running through some of the lines of code, remembering that to get things started, all you have to do is hit play on the code sections. Okay. Now this notebook is a bit of a more chunky one than the one we did yesterday. Some of the activities and things in this take a bit longer to do, but it's quite representative of a real data science project. I'll introduce that properly in a second. So, what do we need for data analytics and for data science to happen? We need well-structured data. If you don't have well-structured and well-behaved data, then you can fall into this garbage in, garbage out trap for data science and get dismissed very quickly. So the data instances or observations, they're samples from a whole population of people. So you can't get all of the data in the world, but you can get samples of that or a proportion of that and then generalize from there. Each of these has many features, typically different characteristics that you're recording from the different people or different entities in there. And it requires a journey from raw data to a single tabular representation. Then you can create reports, visualizations, and classifiers. Now, there are three basic encodings of structured data. Okay, you will have come across this if you're from a computing background, but don't worry if you're not, they're not scary, and we're not going to go into them in too much detail. Okay? So these three basic encodings, one is a table. So it's got, say, an ID on the left or a row number. It's got some information in that. And typically this information is of different types. So some text, some characters, some maybe numbers or number mixes, and different labels. Okay. They're called data frames in pandas or Python, and relations in SQL or database language. Okay. So that's the first basic encoding of data. The second type of structured data are called arrays or matrices. You'll see these a lot later on the course, actually. We're not going to do much with arrays because they end up being a bit more complicated, but arrays behave a bit like tables, but without the ID number, and all of the cells in the array have the same type of information, so that generally all numbers or all text, but it's typically numbers. Okay. So this would be a matrix. And it would be what we call a 3 by 3 matrix because there's 3 rows and 3 columns. Apart from the fact that it's the same types and you don't have an index, arrays are exactly the same as tables. The nice thing about arrays... Hello, sir. The nice thing about arrays is they let you do mathematical operations and are generally very efficient. So we use them a lot in AI, especially when we're doing things like deep learning machines. The third type is one that we saw yesterday, actually, and this is a basic standard encoding of structured data, and that's called a dictionary. So when you're dealing with things like web data, XML, if you've heard of that, or JSON data, It's nested data represented by dictionaries. Dictionaries have a key value pair in the same way that a dictionary, a book on a bookshelf, would have a word and then the definition. So the key would be the word and the value would be the definition or the information about that word, where that value could be a string or an integer, so text or an integer, a number, a whole number or a rounded number, it doesn't matter, or a list of values, or even another dictionary. So you can have dictionaries of dictionaries, and that's when you get more complex data structures, but more complex and rich information stored within them. Lots and lots of public data sets are released by governments in JSON format, so in dictionaries. Okay? So they'll look a bit like this. So they require some manipulation to get them ready to turn into tables or arrays that we can then do some of the mathematical operations with if we want to. And that's what we're going to see today. So this example here is a dictionary from opendataphilly.org, the Philadelphia Regional Government Public Data Set, and it's about geocoded information about traffic violations in some particular location of the city. The data can be split up into subcomponents, which again begin to look like tables. But for this lecture, we're going to focus on tables. So if we're trying to structure data, we're going to go through a data acquisition process, first of all, to get it, then wrangle it, integrate or join it, and then clean it once we've joined it all together. You can do the cleaning at different stages, but you end up often repeating your cleaning processes. So it's best to just do one big cleaning phase rather than lots of little ones. There are certain cases where that's not the best case, but you'll find that with more experience. So in general, we're going to pull data from wherever it lives, which is usually remote and not on our laptop, and turn it into tables. So if we needed to analyze text or linked what we call HTML or website files. So websites are coded in this language called HTML, and that's what makes them look the way they do. So if we're looking for patterns to extract the entities we're interested in, then we may pull data in from a remote database, import a CSV or a comma separated variable, a bit like a spreadsheet, or those JSON files that I just mentioned. Somehow we have to get raw data into multiple different tables. So here we've got text, for instance, as an example, which you can extract based on patterns into a table. If you've got multiple different text files where you've done like a web crawl and pulled information from various different websites like we're going to do today, then you'll end up with multiple different tables. Or a database, you can access a database through what we call an API. API are just a common AI and technical term for pulling data in from computer science into structured data. Once we've got data, we've acquired it and wrangled it, then we're going to integrate it into a single table, and then we'll clean it. So this cleaning can be quite complex or can be quite simple, and it varies from application to application. There are a general set of cleaning steps that people tend to do. It's just that it varies slightly what is cleaned in each data set. Okay. In much the way that if you were to clean my house compared to your house, you would do the same things probably, but it would just be, different. That you would hoover this room rather than that room. You might dust a room in your house, and you may need to do more cleaning in the bathroom of my house, for instance. Once we've cleaned the data, then we can use that data to try and get some understanding or some knowledge and information about it, create reports, visualizations, and maybe classifiers, or use more complex AI tools and techniques. So if we're going to structure data in the context of a web data task, okay, we're going to do this completely application-based today and follow a great example and work this through. So this example is worked out in the Data Wrangling file. So if you're feeling confident, as I say, get Colab up and get ready to work that through there. I'll just put these two screens next to each other so I'm not cycling through. So here's the Colab notebook, and the first thing that it's doing naturally is doing all of the imports. That took a bit of a time to do that, so it's best to get that going first of all. If at any point you think I want to remember what Ian says about this part of the notebook, or just to explain what's going on there, all you need to do to add in an explanation or add some extra comments is if there's a block of text already there, you can add to it. So double click and you can type text here and just do Shift and Enter on your laptop, and that will move on to the next section and save it. You can edit the text if you want to put any extra notes in things, and hit Shift and Enter again, and that does it. Or you can add comments inside the code. So here we've got a block of code, anything with a hash in front of it, that whole line is just a comment for your information. So I'm just going to add an extra comment here. So hashtag import relevant libraries. Okay. So we're importing all of these and installing these things on the computer in Google's cloud. And the reason we're doing that is it doesn't have those things as standard, so we need to bring them in. The reason we're bringing them in is because it's pointless us writing loads of complex functions to go along and search through the web and do our what we call web scraping, so getting information from the web and the internet so that we can then do this data wrangling project. So it's absolutely pointless us going ahead and doing all of that. So I'll just reshare my screen. We might as well go ahead and use the code that someone else has already created to go and do that. Okay, so that's why we do imports and use someone else's functions that are already working and really efficient. So what's our experiment going to be? We're going to be looking at CEOs of major companies. I've got a hypothesis. So that's always a good place to start with a data project, have a hypothesis. My hypothesis is that CEOs, or chief executive officers, those in charge of major companies, are typically in their 40s and older. How are we going to test that hypothesis? Well, we're going to identify top companies and the CEOs and look at the distribution of their ages. If more are in their 40s or older than are under their 40s, then the hypothesis is correct. We've not put any quantitative measure on what this typically here means, so it would be better if we could do that. But we're just going to stick with typically, assuming that more than 50% are in their 40s or older. So we've got some issues here that we need to think through and how we're going to solve these or get past these blocks that would stop our analysis working. So where do we find authoritative data or reliable data? How are we going to load it in? And how we're going to link it together? Because we need to remember, identify those top companies, identify the CEOs, and then identify their ages and join them together. So we're going to go with 3 simple data sources. A file with a big list of companies and categories in comma separated variables, and that's going to be online, someone's already created that for us. A table of companies and CEOs in a Wikipedia page. Now, Wikipedia isn't the most academically reliable source generally because it's open and editable, but as time gone on, it's edited more closely and scrutinized far more. So it's still not a good practice to reference Wikipedia in terms of a dissertation or an academic publication, but in terms of gathering data for a project like this, it can be quite good. Our third data source is going to be content from HTML pages on people, so from each of those CEOs. Okay. So first of all, we need to go and acquire the data, and that's where we're going to do what we call web scraping. So there's a file with companies and their categories. So we're going to fetch this file using this package called urllib and read it in using pandas read CSV file that reads it into a table. So let's go ahead to Colab and go and do that. We've got a couple more imports to do. Okay, that was nice and quick. So we're going to go ahead and get that data. So we're going to request the data from this URL and read it in. That's finished. It was really nice and quick. Now I'm just going to run the next block of code that's going to make sure we've got a connection to a mini SQL or a database that's set up on this server for us, and then it's just going to print out some information. So that was really quick and easy, and we've got information on companies. Okay, so it's got the list of companies, what their names are. It's got some homepage information for them, a list of categories that they sit in, their size, country code. Okay, so quite a bit of information there. In fact, it tells us at the bottom how much information. So that's 47,758 rows and 18 columns worth of information. So 18 different features and 47,500 rows or entries in that database. So quite a lot of companies and a bit of information about them. 18 columns is quite good. It's not anything forensic, but it's a good start. So we've got that data in now about companies and their categories. Next, we need to get a table of companies and CEOs from Wikipedia. Now, Wikipedia stores data in what we call HTML format. So that can be a bit of a mess. In fact, this is what HTML code looks a bit like. Okay, so it's a bit hard to read as a human, but actually, if you look for around some of the stuff that looks like computer code, like these brackets and the weird things that don't make sense, like TH or T-body, the actual words are the actual titles and the sections and the things that are actually shown when your computer looks at the web page. Okay, so we're just going to jump and use the code that someone's already created for us to read data from Wikipedia for us. So that's very nicely just gone straight away and grabbed 185 rows and 6 columns of data from Wikipedia. So that was nice and quick for us. So for each of these companies, and these are all big companies, it's then got the information of who the executive is, what the title, when they became the executive, and some information about them. Now, the problem gets harder when we want to extract structured data. So what we're going to do is then have to find complementary web data. I'll just try and mute everyone there. A second. There we go. So using this information, this data frame that we've got, and this web data that we've pulled in, we need to find additional information on the web pages of the CEOs. So this executive here, David Rowland, we need to go away and find his information, because although it says when he was the executive since 2019, he was the executive of Accenture, the big software company and consultancy company, we need to know when David Rowland was actually born. Okay, so we need to, from this table, extract who the executive was for each of these rows and go away and find their data. So we need to go to his Wikipedia page. So this becomes a bit more of a challenge. So we've got a question just come up. How the specific notes collected from a source like Wikipedia, there must be hundreds of notable points per person. How are the notes showed? So it's extracting structure in a particular way. It knows where to go and look, and I'll show you that in a second, Shemai. That may answer your question. Okay. So from this, it's going to go find the executive name in this column here. and then go to the Wikipedia page for that person, but it's going to go to wikipedia.org/wiki/ and then the executive's name. But if there's any spaces between the names, say David space Roland, it's going to put an underscore. And this is the way that Wikipedia formats all of its pages, so that really helps us. Okay, so if I jump back to Colab, it's going to create a crawl list, and this is a list of all the web pages that it needs to go to. So it needs to go to the Wikipedia page for Julie Suite, so julie_suite.html after all of the other stuff. So wikipedia.org/wiki/kumar_burler.html. You see, it's got all these websites, so you could click on the website and go to it yourself. But if you collect the data yourself, it's going to take you ages, especially for all of these 185 different companies. So let's go and just set Python and then this Colab notebook away, going and finding that information for us. And it's each time saying it's looking at the information, at the file and the information for them. And it's not going to find everyone because not everyone's got a Wikipedia page. So whilst it's doing that and looking for each one, let's just talk about what it's trying to grab. So this is what a CEO web page looks like. So we've got Tim Cook here, CEO of Apple. Okay, he was previously the chief operating officer. You've got lots of information in Wikipedia and text, and it's different for every person. What we actually want, though, is their date of birth, and that's always stored, if they have that information, in the born section of the HTML table on the right-hand side, underneath a picture of them if it has one. So we're looking for this bit over here. So the nice thing is that because Wikipedia always formats its web pages in the same way, so it has lots of text here, a contents page, a side panel with the information that we know we want, and then it's got more text and stuff underneath and information about them, if they're, you know, what they've done previously and all that stuff. So what does the HTML code actually look like? So the HTML code looks like a mess to look at as a human, but our computer and our web browsers interpret it and show us a fully nicely formatted web page. So this is what Wikipedia HTML code looks like. The thing is, we know exactly what we're looking for because it's formatted always pretty much the same way. So we want the side panel, that's this section in here. So we can tell Python to go away on our code in Colab to go away and look for the right section just after where it says born. So it's going to say born, it's got a name or nickname for the person, and then the age or the year. That's the information that we want. And because it's always got the information just after the word born, we can tell Python to go away and always get that, and always get the right thing. If you have done any website development or HTML work before, then you can think of it a bit like this. We've got what we call a tree of information where there is information in Tim Cook's Wikipedia page, but we don't care about all of that. The HTML in its main text sections, we just want the card with the born and the birthday. Okay. Don't worry if you're not familiar with website development and HTML. That's just for people who have done some sort of computing before. So what we're trying to do is just find that card information or the side piece that's just over here, this side piece, to get the born information. Then we can extract it using what we call XPath in this scrapey tool, and then acquire the information. And we'll create a new data frame called execs_data frame. So these are pages. And then if we run the next one, we'll see exec data frame or exec_df, and we've got that information. So for all of the 182 CEOs, we've got the web page, the name, and what their date of birth was, if that information exists. If that doesn't exist, then it's listed as NAT, or not a time. There are a few different ways in computing where we represent things that don't work or don't fit into our nice framework. Right? So sometimes they're not a number, sometimes it's not a time. All that means to us is that we can't format whatever information was there, or no information existed. So it's just listed as not a time. So when we clean the data set, we're going to remove these people, because it would be unfair to include them in any analysis because we don't know how old they are. Okay.
Hi Ian, there's a question on the chat about primary versus secondary data.
So that's a great question, Oliver Sina. So, and it's a really interesting one in AI. Primary data is usually heralded as the best thing if you can get reliable primary data. Primary data takes a lot of time and money and effort to collect normally. So if you can get information from secondary data sets like we have, and we've just gone away and got 181 sets of information in a second, rather than going up to each of those CEOs in a primary data way and going and surveying them and asking them what their date of birth is, which would take months really to book an appointment with them to get that information, if that makes sense. So I know I'm extending the principle to the absurd, but that's the equivalent point. So in terms of time and scope, if you can get what you consider reliable and easily accessible secondary data, then that's generally fine for an AI project. But there are going to be some cases where you need primary data. Okay. So I mentioned learning analytics yesterday, and I've got a few projects with some students, master students from the current MSc AI cohort going on, where they're looking at student, module results and assessment results in some of our degree programs. So some of that information they'll be able to get in a secondary way, as in just look at the data for what the results were. But if they wanted to go away and find out what people thought they'd done, how well they thought they'd done, if they had really struggled with that, if they struggled with the module, or if they just performed badly, they'd need to go away and survey each of those people and get that primary data. That would be a really rich data set, but much more time intensive to collect than to just look at the module results, print the information off, and take a few seconds to do that. So does that answer your question? Feel free to let me know if you want some more information. Great. So we've created a new data frame called execs_data frame. So where we currently are is we have a company data frame, a company CEO's data frame, and an execs data frame. So this is one data frame or table to do with the companies, one then to do with the CEOs, and one then to do with the information for each of those CEOs or executives. So, got two questions then. Is the data clean? And how do we link the data? So, do we think the data is clean? So, tell you what, we'll go full teachery. Well, Shamar, you beat me to it. I was just about to stick a quick form and ask people to vote, but you know what? You've jumped in there with a perfect answer. So, no, the data wouldn't be clean because there's values that aren't found. Okay, so that in that previous slide, we saw that there were some not at times. So that's not considered clean. We can't then go away and do any robust analysis or comparison of these birthdays because we've got some not at times. So what we need to do then is to clean the data. So we need to bring it together and clean it. So in the company's CEO's data frame, we've got these people listed, and in the execs data frame, we've got these people listed. Now, the first things first is they've got spaces between their names there, and we've got underscores between names here, because we had to get that information from online. So what we need to do is to replace underscores with spaces. And this is it looks a bit scary, but all it's doing is looking at each name from a company CEO, and if it's got an underscore, so this line here, it replaces it with a space. In programming, we like to make things look complicated when they're actually just doing something really simple. Control F or find and replace would do the same thing if you had an Excel spreadsheet, for instance. Okay, but the thing is, in Excel, this would be a much more complicated ask. So let's go to the cleaning section. Let's have a look at the data. So this is when they were born and their names. This is a great way of just getting out the information you want from a data frame. That will be particularly useful when you're working as a group trying to do some of the hack on the data that I'm going to give you. So we're going to apply that filter to replace underscores with spaces, and that's creating a new column called clean underscore name, so clean name. So it's transformed Julie underscore Sweet to Julie Sweet, Kumar underscore Burla to just Kumar Burla. Okay, so that's great. Now we can link things up. We're doing the same in the database that we created for the executive and the CEO information. Let's have a look at their clean names. Perfect. So that's sorted. We've done that in 2 of our data sources now. And we can do a comparison check as well. So it's really good to see if a name is equal to something. Then we can just do for all of the elements in this column, clean underscore name is equal to Kumar Burla. So what we're saying is it equal to that? And that's false for the first one because her name is Julie Sweet. The second name is Kumar Burla. The third name is Shantanu Naranya. So it'll be false, true, false, 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 false. And it'll be false likely for the rest of them unless Kumar Burla happens to be CEO of another massive company. That's very unlikely. Okay. So now we have a basic set of operations over single tables. So we've done a little slice or looked at just a couple of columns in particular of our data frames. So that's a useful operation. We've selected things. We've applied a filter to change underscores for spaces. And then we've done an update in terms of our data frames and in the database that we created. So we've got what should look like some clean data now. I'll just run these last things to check that everything's working right. Perfect. So we've got Kamal Burla with his clean name there and his clean name in there. Now we need to join the exec data frame with the company CEO's data frame to get the company information for them. Okay, so we're going to join the data together. So this is these 2 different tables, company CEO's data frame and exec's data frame. So we've got exec data frame has a clean name and when they were born. And the company CEO's data frame has the executive name and the company. Those are the important things for us. So what we need to do is see from this table and this table, we need to match up the executive and the clean name. So if the clean name is equal to the executive, so if they're the same, then we want to make sure that this born information is copied across. So you might have jumped ahead from me, Abdul, but yes, there is an error in this workbook, and that's been left in on purpose because it's a standard pipeline of processing, cleaning, and modeling data that was applied to this data set. And partway through, there was an error that was found. But I thought that was a really great experience for you to see that sometimes your standard pipelines break and you need to do some recleaning or modeling of the data to sort out those errors. So don't worry if you hit a part where it doesn't work. So what we're going to do is join things together. So merge the data that they were born from the exec's data frame into the company CEO's data frame. So that's when they were born from this one, and put that information into this one, making sure that we only do that if the executive and the clean name and the executive name match. Okay, so that's going to create this nice new table for us. Okay, and that'll look like this. So let's have a look in our notebook and double check what's going on. So here's our company CEO's data frame, and that's merging. So we can check the merge there and do that in the database. And then we've got that information all stuck together. Okay. Now we've gone from 181 down to 177 rows now, because there were some executives and CEOs that didn't match. So it's just not done that. Okay. And in the database, it's gone from, instead of doing not a time, it's just gone for none when they were born. Okay. So there's some more cleaning required to sort those values or deal with the missing values. Okay. There were some ways to go back and re-get some of the extra CEOs where things didn't quite work. So it's gone back and done that in the code there. Okay. But this is what we're looking at. Now, we've got our data frame where we've got everything joined up. Well, we've still got some not a times in here that need cleaning. Yeah. So that's something that we entirely missed out with our cleaning. So how do we know if our data is clean? Now, for this case, we've got 181 rows in the data frame. We can look at them one by one. We can eyeball it and see as a human. But if you've got millions of rows and multiple different features and columns and things, you can't be going and eyeballing it. You can't use a human to check that. Okay. Look at the data is always good, but to do it clean, you need to operate some standard rules, procedures, and checks to make sure you know what's going on there. So we need some master data that we know is clean, and we need some validation rules. So master data management will be to gather a complete, correct list of CEOs, store it in this master model, and then compare against it. Many organizations manage this with data governance policies about who can update and how things are added and what's compared against it. Okay, so that will be things where you wouldn't, as a junior AI specialist, have any access to that master data through the data governance procedure. But you can provide validation rules. So names should not have non-alpha characters. Okay, that would be a standard one. Birthdays shouldn't be non-null. Seems fair as a rule. And we must be aware that you may have false positives and false negatives. Can anyone suggest a problem with this first validation rule about names not having non-alpha characters?
Hyphens.
That was very quick, Alex. That was brilliant. So we've got hyphens, yeah. Anything else? So
names in Chinese or other language types.
Perfect. Yeah, names in Chinese, other language types, and apostrophes, Shemai said as well. So the example I have on the slide actually only has the apostrophes and hyphenation. We've assumed that we've got them all in English which Wikipedia normally would convert, or if there are periods, for instance, for initials. So we can create additional adaptive validation rules to account for these cases, but you need to specify each of these cases one by one. Okay, so here's some code to do that. And again, it might look a bit scary to you. Don't worry, I'm not expecting to be able to understand just from looking at it what it's doing, but we can, you know, apply some common sense and see what we think it might be doing. So replace character is Q. So we're going to stick a Q in there if there's a problem, just so that we've always got the same thing. So if there are any spaces, then we're going to stick a Q in. If there's any full stops for whatever reason, we're going to stick a Q in. If they've got a middle name, say O dot. If they've got a backslash, we're going to replace it, or a hyphen, we're going to replace it. Okay. If there are any illegal names, then as far as our rules go, then it's going to say that it's failed, and then assert or shout at us, this has failed, I've found some illegal names. So let's see what that does. It's failed. It's found some illegal names, and these would be the illegal names. Okay. So we can go back and work around these, and we're going to match them approximately. So we'll just run the code. You'll learn far more about these kind of things when you go into the applied AI module and are taught about natural language processing tools and techniques and tricks of the trade almost in natural language to get around where people's names are shown as things like this. Okay, so let's have a look at what the exact data frame looks like now. So we've got the clean names, we've got when they were born, and we can join it back into the table. Okay, merging it all together, we've got their updated information there when they were born in this column down here. So we've joined together all of our data and wrangled it all. Perfect. Okay. So what about null values? We're not going to worry about those too much. Okay. You could go and look for more information, search different sources and things, and drop them from the table, but we don't have to worry about them too much because our Python code is going to naturally sort this for us when we do some plots. That's going to tell us whether or not our hypothesis test was true. Okay, so let's just go ahead and visualize the result. Get ready to plot. So that just tells it to prepare to do a plot for us. It's going to look at the total information. Remember, we've still got some of our information missing from our not a times, which you could clean out. Group them by this information. Get it all ready for us. And then start counting if we've got their information. Okay. Make sure the database is counting, and then we're going to group them by which decade they were born. That'll be quite easy for us then to see if they were over 40 or not, based on the fact we're at the start of our decade. And then we'll plot. And, well, hey, it's worked. We've got a nice chart here. Let's zoom right in so that we can see this more clearly. So this is the chart and the end of our data wrangling, cleaning pipeline and process. So we've plotted our data by decade. So our original hypothesis, if we go right back to that, was right here. CEOs of major companies are typically in their 40s and older. And our analysis was going to be to identify top companies, CEOs, and look at the distribution of their ages, or the groupings of their ages. So was our hypothesis correct? What do we think? Why do you say yeah?
Because the majority are born before the 1980s. In fact, most of them are 1950s. So they would be in their 70s now?
Yeah. Completely right. So most of them were born, even the ones that were born in the 1960s would be over 40 now. So some of them at least. But most of them, yeah, 1950s and before, if you counted them up. So this grouping here, more of them than on this side, therefore our hypothesis was correct. Would you assume that it was completely correct? Any caveats that you'd like to throw on that?
The number of missing dates.
Yep. So missing dates is going to potentially bias the data set. We don't know how it's going to bias the data set, but we just know that there's a weakness in our claim. Any other issues with our hypothesis or the results that we've got? So our hypothesis, let's just be really, really, really scrutinize. Okay, so where's the data collected from? So yeah. There may be some weakness in where the data was collected from. So that's a great suggestion, Mohammed Ahmed. Let's just go word for word through. CEOs of major companies are typically in their 40s and older. So this bit, yeah, we've checked, and we can say, based on the data that we've looked at, so that we could collect information for. Perfect. What was our classification of a major company? That wasn't clear in our hypothesis. So that's a constraint in our assertion that our hypothesis is correct. And this is something that's really important, and that we try and hammer in over the whole course, especially when you hit the impact of AI, the end module, think about ethics and pipelines and the impact of what the AI is that you've done. Like, yes, we may have proved our hypothesis correct, but we've proved it for the data that we could collect, relying on that being robust, based on our assumption of what the companies were major companies, and based on all the data that we could collect, ignoring the data that we couldn't. So there are 3 easy potential weaknesses in our analysis there. You need to be mindful of those and be able to think, do we robustly think that those question or allow people to question or discount our analysis? That's really important from a statistics point of view, as organisations like the Office for National Statistics in the UK have to put a lot of effort and work into finding the limitations of their studies and their analysis, because they get used by politicians, by the media, by the public as gospel sometimes. And if they don't highlight the deficiencies or the weaknesses and are able to defend them, then they can be used either way by either side of an argument. So yeah, Oliver Senior, you could make a more direct or technical hypothesis. Generally, people like to make general statements though as hypotheses. Yep. So there is an exercise, Sahik, there if you're interested. Now this is quite hard. So if you've got a background in computing or are comfortable with the work that we've done today, then I'd encourage you to give this exercise a try. But don't worry, for most people, this was an exercise put there from the IBM course. Okay. So Shmai, so we would also have to have a benchmark for the market value to find what's classed as major. Yeah, absolutely. Typically, you wouldn't. It would be hard to be scrutinized if you'd use, say, the Fortune 500 or the S&P 500 companies in the US, for instance, or the FTSE 500 in the UK. So they're generally agreed to be the major companies in a country. Okay. So in a very short time, we've managed to go through Wikipedia, search for a list of large companies, join that together with a list of their company CEOs, go and find out when their CEOs were all born, join them all together, plot it out, and test a hypothesis of quite a general statement. If you had to do that without the code, that would be a day at least of a project to go one by one to each of the major companies' websites to get the CEO to then go from there, click on their information, record it all in a spreadsheet, then try and do any analysis of that. Simple things like these assertion statements. I'm just going to scroll up to where we were doing our data cleaning, for instance. Although you can do a find and replace can be a bit clunky and not overly reliable in things like Excel. So to do the same experiment without code and without Python or our data analysis would be a far more extensive and difficult task. So that's why we have to learn to code in AI and data science. And this is the thing, on our AI course, we do teach programming and we expect people to do some Python programming as the standard programming language in AI. And the reason that we try and get you upskilled in that is because of the benefit in terms of time and the requirements for data analysis projects, often needing a technical programming language. There are pro AI tools and techniques, especially prominently by Microsoft and some from IBM, where you can just upload your data set, drag an AI model in, drag a cleaning pipeline in, and see what happens. And you can click and go. It's all, click on this, tell it to do that, job done. And you don't have to write any code. The thing is, it's simple, it's not overly reliable, you can't test it very well, and you can't do any of the nitty-gritty stuff and get under the bonnet and see what's going on with stuff like this. So that's why you need to learn Python. Okay. Does anyone have any questions about what we've done this morning?
The error that was in the code and I can't remember who it was that pointed it out, by the same thing going ahead, and you said it was a known error.
Yeah, so Abdul, you got a known error from the XPath. So I think I may have skipped over and not run the line of code that actually gives you that error, but there is a line of code in here that I've left in that gives you an error, and it's one of those good teaching points that we don't often. We can say to you, here's a worked example of something, and it's worked example, therefore it works, and that's really nice. And then you think that it'll always work like that, and then you go out into the real world, try and do the same thing, and then it breaks on line 3, and then you go, well, and my code's broken on line 3 out of 100 lines. What on earth do I do? So it's a really good experience for you to see some of those things. The error that it had, I believe, from the non-type and the XPath was one of these paths where it was trying to find information from Wikipedia for a certain person, and it broke, and it didn't work because the link was no longer existing for some reason, and it wasn't handled properly by Python. So that kind of thing happens sometimes. The nice thing is we could just move on past that and not worry about that. Okay. If you want to find it especially, so the easiest thing you could do is go on the workbook. If you hit edit and clear all outputs, and then just hit run all, and rather than clicking one by one on each of these sections of code, it's just going to run them all. Okay. I'll just need to give it a minute for it to actually do all the imports to start with. The biggest thing is installing the scraping tools and the way of getting the information from Wikipedia. But the nice thing is, all of this stuff is done in the cloud. So it's done on one of Google's own computers. They're giving you for free. So it doesn't slow down your computer at all, pretty much. Just having Chrome open is the only overhead for you. So it's quite nice to be able to use Colab and just set that off going with an AI project, and then coming back and doing something, writing a report or checking your emails or doing all the other stuff that you want to do. Whereas if you're doing some of this stuff on your own computer and running it all locally through an application like Spider or Anaconda, all of a sudden that becomes quite cumbersome and can really slow down your machine. Okay. Shamar, you've asked, we'll be using Colab. Yeah, so I would definitely recommend using Colab, if nothing else, because you can nick some of my code from some of the sessions that we've done over yesterday, today, and tomorrow in the hack when you're working together as a group. So, Abdul, great question. For all data sets in general, do you have to follow the same rules and process? So it depends what the hypothesis is and what you're testing, really. But if you've got a situation that you're framing like this, so you've got you've got major companies who have CEOs. You need to get information about who their CEOs are from the list of major companies, and then from that list of CEOs, you need to take those CEO names and then go and get their dates of birth, and then join it together, clean it. So that's your standard pipeline if you've got information in multiple different tables that need joining together. And that's quite typical if you're doing any sort of web scraping, web crawling, getting text from multiple information. Amir, you will absolutely learn some of this coding and all the coding that we require from you on the course. Okay, so don't worry that you don't understand what this code is doing. Some of this stuff is quite advanced, and it's nice that the IBM team have provided it for us. But if I was teaching a mod, like using this as an exercise partway through one of my modules on the MSc AI, I would give you the code and say, this is the code to create the database and to join things together. Okay, it might be up to you to write the code to do, say, the replacing of things. So if I say to you, some of the data has names in it where there are apostrophes, for instance, or slashes and things, you might need to go away and write this code. Okay, and there's loads of different ways that you could do that, but you'd be upskilled and confident enough in programming to find out how to go and do this. It might just need a simple search online to go, how do you replace spaces in a Python data frame? Someone on Stack Overflow or online will have told you how to do that. So Edna, do you use SQL query in Python, or is there a special process to connect to a database to Python? If you're using a full-on database, Edna, yes, there is a special process. If your database is, typically those are local, so they're on your computer. And if they're on your computer, then you need to be using a Python program to connect to it on your computer. Okay. Now, what we've done here is got a mini SQLite database, if you're familiar with that. So that SQLite database is contained online inside the server, and it can do that from within Python. But in Python, you can't just create a whole database and manage it the same way that you could locally on your computer. Okay. So you can connect to an online database quite easily if it's accessible online. There is an example of one of these IBM notebooks which uses what we call a NoSQL database, or MongoDB, if you've come across that. But that's a more advanced database structure that we cover on the first module of the course. But that database has to be set up accessible externally, and then the lab notebook connects to that and works from that. Now, I haven't got that set up and things, and actually it wasn't worth us spending the time doing that, in this hack at least. Okay. Does anyone have any other questions? Yes, Abdul. So if you've got a data pipeline where you know you need to merge tables together, you can merge them in the same way. You just need to be careful about, which column you're merging them by from the data frame. So here it was merging CEO names and clean names, for instance, or exec names and clean names. Maybe it's something else. If it's a parent company and you're looking for a child company and how much the child of each parent company is worth. So you've got a different search term then. Okay. So if anyone's got any other questions, feel free to post them in the chat. But otherwise, I think what we'll do is take a short 5-minute break there. And then we'll move on now that we've done our data wrangling and finished. So we've got the plot and we grouped it together in a set of nice bins. Okay. So we looked at the basic mechanisms for getting tabular data, extracting data from the web, merging the tables, linking them, a bit of basic data cleaning, and some simple grouping and visualization. Okay. If you want to have a go through quickly in the next 5 minutes or during our lunch break, have a go through this Perlab notebook and just make sure that you're getting the same plot out as me. Okay. Otherwise, just go and grab a drink, and after our break, we'll come back and we'll be looking at some sort of data visualization aspects for exploratory data analysis. Okay, that is a brilliant suggestion, Yasmin, thanks. So if you don't have any coding skills, Yas and I would completely recommend and endorse looking at W3 Schools, Python, or Code Academy before you start the Masters, just so that you have a feel of what Python is and general setup. Okay. So we'll pause there for a 5-minute break. Hi everyone. So thanks Abdul for resharing those links. And Yasmin, great suggestions for the Code Academy and the Code First Girls. Yeah, completely endorse those two. One additional Python course we recommend is this Python for Data Science, which is designed as probably similar to some of the ones that Yasmin has shared, a first few steps in Python in programming, getting you used to doing those first few activities before you start the course, really. Okay. So I think it's probably worth just doing a bit of a, the teacher in me wants to do a bit of a knowledge check just to make sure everyone's doing okay and following along. So I think we'll go for, this is a first question that I'll just shove in a couple of them, but does anyone have any questions, any AI broad topics or things that you want me to discuss whilst we're here? Any curiosities or things that you want to know if it's included in the course? Or are we all just happy carrying on?
I've got a question about the group hack.
Yep.
So a lot of the Python you just showed us was a little complicated, well, for me anyway. It looks quite intense.
Yep.
I'm wondering to what extent we're going to need to, how clued up are we going to be in time for the group hack? Like what kind of stuff are we going to have to do?
You're going to be really clued up, don't worry.
Okay, cool.
Yeah. So what we're going to do tomorrow morning is going to be, I'm going to give a brief an introduction, obviously, to the hack to the data, and I'm going to show you an example where I manipulate that data. It's data of temperatures of cities, capital cities across the world. So it's quite a data set given how many capital cities there are and how long back the data's been recorded. So there's plenty of it to look through, to sift and to modify and things to clean as well. And but I'm going to show you an example just focusing on an individual city and do a bit of a cleaning pipeline on that and plot and then show you. And it's then up to you as a group to say, okay, Ian, you're giving us this plot. So we could recreate this with other cities if we wanted to, but it's up to you as a group what you define as an important question or finding that you want to share. So maybe it's the change in the minimum and the maximum temperatures over time, or the average, or the difference between that, how that's changed over time. So if temperature's getting more extreme or less extreme over time. Maybe if there's surrounding cities that are in a close geographic area that have vastly different temperature profiles over time. So it's up to you what you explore and what you want to focus on and try and show in that little presentation. But I will show you how to do it on an individual case. But no, absolutely great question. So it's because it's going to be done on that and dynamic and numeric data that you're going to be given as a CSV file that you just upload to Colab and off you go. You don't need to worry about any of this web scraping and stuff. This was just showing you what data wrangling is, joining stuff together and thinking about how you want to join data and be a bit careful with that. Make sure that you do some of the cleaning stuff as well. Okay.
Okay, thanks a lot.
So Ashraf, great point. So every time that we introduce an API, generally we need some sort of a login or system for the ones with rich and reliable data. So that would require me setting one up and then sharing my login details with all of you, which goes against lots of the privacy policies of these places. So in order to do things fairly robustly, rather than say to everyone, right, you all go and sign into this API, this system, give your personal details across to them, which is a decision that you would have to make yourselves. I didn't want to force anyone to have to do that. So naturally, I've just gone for a very simple data example with this Wikipedia. But on the time series course, there is one example where I get data on oil prices for like change point detection. So looking at a time series of data, a series of data, and then going, well, in this part of the data, it's all going up and down quite normally, and then all of a sudden, well, there's a spike in the price. There's been a change in the fundamental times or data source. So for that, we're collecting data using APIs. But it's good that you're aware of them. Okay, so question that I asked, I'll just give it 1 more minute for people to respond to that. And just 1 more after this one as a brief knowledge check to see how I'm doing, how you guys are following along, and then I'll go through the answers. And see if you can see that innocent when it comes through. Okay. So first question, we had what makes data big? So we had several options there. The size of items in the data set, number of items in the data set, number of important dimensions or features in the data set, the speed of change, or the heterogeneity. Now, in and of itself, the size of items in a data set doesn't make a big data. So if you've got 5 Word documents to analyze, and each of those Word documents is 100 pages long, have you got big data? Well, not really, because you've just got 5 Word documents. It's more to do with the number of entries and how quickly they change in things, rather than the size of what those entries are. Generally, there are obviously cases where you could look at collections of collections and things, and a hierarchical approach if you're familiar with that. but in general, so it wouldn't be the size of items in the data set, but the number of items in the data set would be correct. Number of important dimensions or features in the data set would be correct. The speed of change would be correct, and the heterogeneity, or how the variety of that data, is generally correct as well. So if you answered any of the options 2 to 5, well done. Okay. What is a feature? We had 24 people voted for a measurable characteristic and no one voted for a level of uncertainty. So well done, 100% right there. And our final one, which of the following is a big data analytics task? So we've just done data wrangling, so we knew it was data wrangling was going to be in there. Cross-validation is another data analytics task where it's sometimes seen as a more of a data science aspect of validating and checking that your AI model is working as it should be, testing it and things, but in general that falls under the analytics and big data analytics. So that's included as well. So if you went for all of the above, well done. So what we're going to do is exit from our data wrangling presentation, and we're going to move on to the data visualization aspects. Okay, so I'm just getting everything up. Okay, can you just let me know if you can see the slides on the screen, please? Perfect, excellent. So we're going to go on for a little bit about this, and then we'll take a break between this and the next, before we move on to the Colab notebook for this one. Okay, so let's go back. Information visualization, or visual analytics, is a really big and dynamic field, and it's so important for data science and for artificial intelligence. I'd argue that the data visualization and the storytelling, if that part is done poorly, then the entire analytics or data science project that you've done is possibly wasted. Okay, you could have done the best work in the world. If you can't convey that to people, get people on your side, or to understand the impact or the importance of that work, then it's a waste of money as far as your employer is concerned. That's why we try and teach it up front. So we teach data visualization as the second module. In lots of universities, they teach it late on because it's sort of a, oh, you know, we've done all the AI stuff, oh, now you can do some data visualization. But actually, as far as I'm concerned, it's really important, one, to have this as a foundation for you, but also for you to be able to visualize data when you're working with it, so that when you're doing the complex AI models and using, you know, machine learning or doing exploratory data analysis and things, you can do proper information visualization so that you can understand what's going on in your data, and it gives you more confidence, especially useful from a conversion point of view. So, as I mentioned yesterday in the overview of the course, we are going to be going back to basic stuff like what is a bar chart, and but teaching it properly, motivating it. Okay, so don't worry about the levelness of that. Now, charts, graphs, visual interfaces, they help. They give us a human way of understanding vast amounts of complex data. There's then an important aspect of that that we need to make sure that the graphs, the charts, the visual interfaces are giving a robust and truthful representative that's humanly interpretable. Our brains are the most powerful pattern processing devices in the world, but at the same time, they can be some of the most easily fooled pattern processing devices in the world. Anyone who thinks that's not true, just go and look at any optical illusion and you'll be convinced. So They provide a holistic sense of data as we load and we analyze it, and your data analysis pipeline should include multiple visualizations if appropriate. Now on that wrangling one, it wasn't appropriate. We just did the whole pipeline process and then visualized to then check our hypothesis. In some examples, if you're dealing with numeric data and you've got to do a data cleaning pipeline that's more involved than what we've just done, well, it's good to visualize the data first, then do a bit of cleaning, visualize it to test it and to check it, and then finish off cleaning and then visualize to confirm, to see what the impact of the cleaning is. Okay. So they illustrate algorithm performance as well. So runtime versus data size and various machine learning parameters or different, in essence, the wheels that machine learning algorithms turn to try and make sure they suit and solve a problem appropriately. So you can visualize those, and that gives us a humanly approachable way of trying to understand what AI is doing. That's really important when we're in an age where people don't trust AI, machine learning things. You can also present information as part of a report or a dashboard. So rather than just designing a chart or a graph to work in and of itself, you have to make sure that it complements the whole dashboard. And that's definitely an art and takes a lot of experience to build up. So visual analytics is an entire research field in and of itself. There is a journal of information visualization. I actually have a paper in there which will be presenting to people, not the paper, the actual journal, to make sure that you're using peer-reviewed and recommended methodologies when you're creating data visualizations. So there are major groups in this at University of Washington, at Stanford, at Maryland in the US, some of the big Ivy League universities. Then visual analytics is the science of analytical reasoning supported by interactive visual interfaces. So ideally, our visualization should be immersive and interactive. So it's a mixture between data analytics and human-computer interaction, or HCI, you may have heard of, and perception and computer graphics. Often interactive visualizations wherever possible. And although you may be an AI expert, sometimes it can be more valuable, rather than perfecting your machine learning algorithm to get that extra 10% classification accuracy, it may be worth you spending more time adapting the colors to make sure that your chart tells the story properly. Okay, I had to do this quite recently with a company that I've been working with alongside some of the MSc AI students, where the end product ends up with this web system that has some charts on, and to them the client wanted to make sure that the visualizations looked just right. So we were changing colors by 1% of green or blue or red just to make sure they were just right for the people that were going to be using the system. And that was the most valuable thing to them. So what is effective use of visualization for data science? Okay, we're going to introduce three main methodologies here, and they're going to be standard ones that are used by data scientists that are like a base level that you should be able to use. And then throughout the data visualization module, we'll push you to more advanced tools and techniques, which will put you head and shoulders above other data science and AI professionals from other universities. So Matplotlib and pandas, they're closely coupled. So we found that in the data wrangling notebook, where we got to the end and then to do a plot was just very easy. We just said plot it. So the data frame dot plot is the code, and you can tell it what kind of plot to do and all the other information. But in essence, it's very simple that once you've got the data loaded in, pandas, this library, and data frames work really nicely together. You need to make some right decisions, though, to make sure that you're conveying information appropriately and in the best way for that application and for that audience, but also from an editorial point of view to make sure it tells the story you want to be told. So is it a line chart like this, or is it a bar chart if it's based on complete data, for instance, or data that you can put into little individual bins, we call them, or groups? What if it's statistical or sampled? What ranges and scales do you want to use for the axes? And do you normalize the data to make it group around 0 or around 1? As soon as you start normalizing it, you need to make it clear to the audience that it has been normalized, because that can skew people's perceptions of what's going on. So let's contrast bar charts and line charts. So if you've got categorical, or data that fits into some nice simple categories, for instance, these companies and how many years they've been running. If you've got that type of data, then you want to be using a bar chart. If you've got continuous data, though, data that can go up and down, yeah, so visualization is all about the graphs, yes. So data that can vary and can be any number and doesn't have to necessarily be a whole number like the number of years, then you generally want to use something like a line chart. So these bar charts are categorical, so they're discrete valued, we call them, often non-numeric, so not numbers. Line charts are what we call continuous data, so they go along a continuous scale, and the lines are what we call interpolated, or we join up the lines between the points. Okay. So how do we choose our axis, minimum and maximum, and scale? Do we want to use a linear axis or a log axis, for instance? So if it's the years since it started, the company, the year it started in, we don't want the scale going from 0 to 2021, because it's very unlikely that any of these companies were started in the years between 0 and 1750, let alone between 1750 and 1900s. Okay, so we can just get rid of all of this aspect of the graph, of the bar chart there in the scale, and move to something more suitable like this in the blue on the right. But remember that the way that you choose the scale changes what's being told there. If your message is that these companies have been around a long time, then for some of these it tells that story. But it looks like Canonical Limited hasn't been around a very long time at all. So changing the axes to suit that, maybe, if that's the message that you need to get across. There's this idea called linear and log axes as well as the scale. Now this was often used in COVID data. Sorry, so in COVID data, you can either use a linear axis, so one that increases constantly along the same scale, so from 10 to 20 to 30, going up by 10 each time, or it can go up in certain powers. So you could go up from not to 10, 100, 1,000, 10,000. That would be a log scale. Okay. Then there's normalizing the data that we need to be conscious of. So if we've got two different tools or techniques, a baseline and an alternative, and we want to show that the alternative is better than the baseline, maybe we need to normalize that, because this scale that we've got on the left here doesn't really allow us to see how much better the alternative is than the baseline for the second company. Just seen a question coming about that, a linear log. Yeah, so yes, Shemai, linear could be, I'll put it in the chat as well so it's completely clear. So a linear could be 10, 20, 30, 40, 50 in plus 10 each time. Log could be 0, 10, 100, 1,000, 10,000. Which would be timesing 10 each time. A log is very good if you've got wildly varying statistics to try and get them on a reasonable and interpretable scale. So when we're looking at things like COVID, more the infection rate rather than the mortality, but the number of people with COVID, you don't want to have a scale that goes constantly up and down and up and down and up and down, and at its peak be really high and everything else be really flat. So the log scale helps you show the peaks and the curves much better and the growth. You just need to remember that you're looking at a log scale. So if we take this data and normalize it so that the baseline is always a value of 1, and then we can contrast what the alternative would be, we get this. So we can see contrast quite easily the alternative with the baseline and see that it's always an improvement, but particularly for case number 2. So what's wrong with this figure? So yes, Shemai, you're right. It would depend, linear or log. It would depend on the type of data you're using and the application things. Okay, now I'll elaborate more. I'll jump back and elaborate more on the normalizing data because that's important. So we've got 3 different things being shown here. So we've got company 1, company 2, and company 3. They've got a baseline thing that they're doing as standard, and then an alternative way of doing something which results in a lower value. We don't need to know what the value is. We don't need to know what they're doing. We just need to look at the visualization and say, based on this visualization, can we see how much better the alternative is than the baseline? And for like case 1 and case 3, you can kind of see better, yeah? Case 2, you've not got a clue if the alternative is better than or worse. So we normalize it to say the baseline, or what they're currently doing, is a value of 1. And then we divide the alternative by the baseline number. So that the baseline of 1 for company 1, we can then see, the alternative is 90% of the baseline. So it's a 10% improvement. Here it's a 40% improvement. Here it's about a 15% improvement perhaps. But you can visually see that really easily from this graph where it's normalized so the baseline is always 1. So we've just changed the scale of the axes to be maximum value 1, minimum value 0, but they all start at 1. Does that make sense, Edna? Great. So, can anyone suggest what they think is wrong with this figure? Yeah, it doesn't say what the scale on the y-axis is. It doesn't give it a title, so let's just assume that's milliseconds in terms of like computation, like executing something on your computer. Any other ideas? What might be fundamentally wrong with this graph? Yeah, so Oluwasini, you're completely right. The increment is not of the scale is not steady or constant in the x-axis. So that's trying to give you an ambiguous graph there. It's making it look like if you then plot it on, it would increase exponentially or grow rapidly. So that if you increase the scale even further, it would go much, much higher, off the chart. And that's not the case at all, actually. If we plot them as just points, we can see that it's a nice straight line. So there's a proportionate increase in scale gives you a linear or a proportionate increase in execution time. This is really important to understand, and lots of graphs are given with mismatched scales and things when they're trying to give a marketing or a ploy. The oil industry has been found particularly to be good at doing this aspect, trying to make graphs look like that to be exponentially better or worse over time, when actually if you just draw the graph properly, it tells an entirely different story, and it's often so that they can hide damage to the environment or the impact, you know, of economic sanctions and things. So great work, everyone who got that. Okay. So you need to think about the interpretability when you're doing any visual presentation. So think about scales. If there's any statistical analysis you've done, you'll need to show confidence intervals. So I'm 90% confident in this analysis, and that would mean it's between these two values, not just that it is this value. Okay. What size font you should be using for point-based methods. Make sure there's adequate white space or black space if you're going to use a different color or something else behind it. Slides don't always have to be black on white, and you get marked down if you're using black on white in the data visualization module. Making sure that color is your friend in terms of there, so make sure that you've got distinctive but tonally compatible colors. Okay. So light text on a dark background or vice versa is always a good thing to do. Try and avoid things like red, green, and other forms of color blindness that may be a problem. One of the other researchers at the university is colorblind, and it completely messed up my visualizations when I was trying to do a presentation and talk to him about things, and he of course didn't understand, he couldn't interpret the graphs very well in the same way. So it just highlighted to me the need to make sure that it is suitable for the audience. And then printability as well. If you've got something, you know, odd color may just map to grayscales if you print it out black and white. So if you want to make sure that people can print something, make sure it's printer friendly. And there's choosing the right type of chart for what you're doing. So maybe you need to have a point chart, maybe you need to have a line drawn through it, but make sure that line is entirely clear where it's going through. Okay. Make sure the scale is suitable. If it's a map or some geodata, make sure that that's clearly represented on a proper scale of the world. Okay. Think about whether it's worth having points or dots or a line that's continuous and joins those up. And start contrasting colours if you're trying to tell a story like that. Say the scores by gender, making sure that you're clear the disparity between men and women for a certain test. So these are just some general rules of thumb. Okay, but as I say, we're very early on at the moment. We've not even started the course, and especially not the data visualization module. Okay, so I'm not going to be too worried about the quality of the visualizations that you're choosing, but more just think about the way that you're trying to show data when you're doing the hack. Okay, but as I say, we'll get to the point where I'll show you what the data is, explain how to clean that and some of the processing behind that, so that you can then think of what kind of things you want to tell, what story you want to tell from the data, and then think of what type of graphs would suit that. Okay. So what we're going to do is break for lunch now. We've come to a natural stopping point before I move on to talk about some of the more adaptive visualization tools inside Python and the little IBM notebook to go through for this session. Okay. We're going to have plenty of time this afternoon to start talking about machine learning and AI tools and techniques from a very basic and introductory point of view. Okay. If you've got any questions that you want to ask anonymously again, please email my email address. I'll just post it in the chat again. And make sure that you start with the subject line question so that it comes to the top of my inbox, and I'll know to look at that, because as I said, I'm getting a lot of emails at the moment. I want to make a priority of getting back to you all. If you have any questions about the applications process and things, there's possibly not a lot that I could do to help. If you're waiting on an offer or waiting on some information or sorting stuff out, the best thing you can do is get in touch with the admissions team, and they can help you through that. Okay, but thank you everyone for attending. We're going to take a break now until 1 o'clock, and then we'll get started on some more technical visualization aspects, and then look at machine learning. Okay, I'll stop the recording there. I'll make sure it's added to the YouTube channel for people to review afterwards.